$1 million in prize money is on the line in the first ever head-to-head autonomous racing event to be held at the Indianapolis Motor Speedway in October. UVA Engineering's Cavalier Autonomous Racing Team will compete with other top universities for bragging rights as the best autonomous racing team in the world. Buckle up as I, your host, Chris Tyree, and UVA Engineering professor Madhur Behl take you in the shop, under the hood, and around the track in this new world, pushing autonomous vehicles to their limits.
When you and I drive, we don't even think twice about knowing what is a vehicle and what is not a vehicle. But to a computer, if you give it an image and ask it, find a vehicle in this image, it's going to have a very different approach, a very actual non-human-like approach towards solving that problem. Because what is an image? I'm getting a little bit philosophical here, but an image is just pixels, each of which has a value from 0 to 255 or some color range value. And so we have to look at a big box of different numbers and figure out what pattern of numbers resembles the car most. And the way we do that is by using computer vision algorithms in this case. I think the simplest way I would describe an algorithm is it's like a recipe, right? So you want to cook a very delicious meal. If you follow the instructions like your mom has provided you and you have the right set of ingredients, it all comes together very well, and then you can enjoy that meal. In mathematics and computer science, our meal is what we want as the output. For example, a very simple algorithm that is very useful for all of self-driving is to know if there's another vehicle in front of you. Right? So that's the goal of my algorithm. That's the meal I crave and desire. So what are the ingredients for this algorithm? The ingredients would be the data that would help me determine or allow me to mix and match things together in order to achieve this goal. So in this case, my examples of this data could be images from the camera, or the footprint of what the LiDAR or the laser-based rangefinder is seeing in front of the car, or the radar is seeing in front of the car, because these are my proxy senses. We don't have a human driver, so we rely on the sensor data to discern what the scene looks like in front of the car. And then we follow a recipe, just like you do in cooking, right? We have a sequence of steps where we take the data, we massage it, we transform it, which is another way of saying you want to be sure that what you see from the perspective of the camera is consistent with, the car is a big body, a rigid body. It's much bigger than the camera. So my camera might say the car is 20 degrees to the left of the center of the image, but that's not useful information to me. I need to know where is the car with respect to the front nose of the car, or where is the car with respect to my kind of the polygon which describes my entire geometry of my vehicle. So we need to transform this data. So there's many different family of algorithms which are used all the time in robotics, but if you follow the recipe as prescribed, you should get the meal you desire. Mathematics is underpinning all of what is happening on the car. I have mathematician friends, and they describe their field as the mother discipline, and they disagree with their physicist friends. But I like both of them. I'm a huge physicist myself. Everything at the end of the day has to do with how do you handle data, which is some numbers that you are getting. And finding patterns in those numbers is usually what the name of the game is, more often than not. And so there's branches of mathematics that we deploy, going all the way from what you studied in high school in terms of just basic geometry and algebra, to where it gets a little bit more exciting when you use calculus, for example. So obviously we rely on these fundamental branches of STEM, and mathematics in particular. And then we deploy a lot of computer science knowledge behind it. So I spoke just a moment ago about how you build together a recipe. You may want to ask, well, what are the different ways of building this recipe together, right? So maybe there's 10 different paths to getting to the same meal. Then there's a notion of optimality, right? What's the best path to take? What's the one which will compete in the shortest amount of time? What's the one which will use the least amount of computer memory? Because if you don't pay heed to these kind of attributes, then you may end up with an algorithm that gives you a answer, but maybe not necessarily the best answer, or maybe it gives you the best answer but takes forever to reach that. And when you're racing, time is of the essence, right? So you have to come up with ways to combine these mathematical operations together in a manner which can be executed very, very fast, almost with guarantees that it could finish within 25 milliseconds or 10 milliseconds. Otherwise, it's already lost. There's no point in even getting any answer. And you just skip on to the next data frame and so on and so forth. So what is computer science, right? It's essentially the science of processing information. That's one way of describing what computer science studies and does. Of course, there's many facets to this, and I'm oversimplifying it. There's the hardware aspects and the data science and the machine learning aspects and the computer architecture, and there's many subdisciplines. But in a nutshell, every computer scientist is working on parsing information, or how do you have a scientific approach up towards passing information towards the point where it is useful, you can make decisions on it. And so there are some rules and some general guidelines which help you do that. And so without going into too much jargon right here, you have different families of algorithms. So you have like search-based algorithms where you are interested in answering, can you find me this pattern if it exists in my data? You have what you call randomized algorithms, where you are saying, I'm going to try different things, and based on their responses, I'm going to know which direction to proceed if I want to get the best answer. So you have many different flavors of algorithms, which essentially, at their most canonical form, are mathematical operations put together in a way that leads you to whatever goal you want to achieve.